All right, so we have chapter 7, which is conservation of energy. And this chapter is, we can think of like a little bit of continuation of chapter 6, where we learn about the energy, where we learn about how we can transfer energy of the system to the system or out of the system, and how we can, um, let's say, convert energy from one type to another. Let's say if you do work, you can have that energy going into the changing kinetic energy of the object and basically being able to then or store energy as a potential energy and all of those things. So in this chapter, we're going to be learning about conservation of energy and what are the conditions where we can assume that energy can be conserved, which means energy before and after is constant, is the same. All right, so we can start with a non-isolated system. Because right in a non-isolated system, energy crosses boundary of the system due to interaction with the environment. It means, for example, if you have a box and I take the object or my system to be the box, right? So if, for example, somebody's pushing the box with some applied force F, well, that force is an external force, and it will change the energy of the system if it goes from A to point B, right? We learn about that. And here's the work done by this force. And the general equation is F dot dl, right? So that's the equation for that force. This is the work done by that force. And put it like here, F. All right, so which means that if you apply some force and it changes position, then you do work. When you do work, this is a non-conservative force, right? Basically, it's a force done by some applied force. The energy of the system then changes. As energy of the system changes, then according to work kinetic energy, right? That energy can go into kinetic energy. So you can say interaction of a system with the environment is work done by external force, and quantity in the system that changes is kinetic energy. Then we can say this is equals to delta K. This was what the work kinetic energy. All right. So what it means that we can transfer energy into the system, and energy of the system would change due to the work done by this type of force. Okay. Um, and we're going to see, right, there are several ways we can transfer energy. So methods of energy transfer is the work done, which was, entire chapter 6, which is transfer energy by applying force and causing a displacement of the point of application of the force. So, but this is not the only one that can do work or they can transfer energy. There's also mechanical waves, allow disturbance to propagate through a vacuum, through medium. It can also propagate through vacuum. So one of the things we have is that when you generate a wave, like a sound wave, a light wave, or a stream wave or water wave, those are actually energy transfer mechanism, because energy in waves can then propagate with the wave, and you're basically transferring energy. There's also, and we're going to be learning about that. We're going to be learning about that. And there's also heat, which is also something we're going to be learning at the end of this semester. And that's the energy transfer due to the change difference in temperature of two objects. We're not considering that in those two in this chapter, but what we will see here is, those are some of the things that we can do. There are more. There's also a matter transfer. So matter physically crosses the boundary of the system, carrying energy with it. This is every time you go and fill out your car with gasoline. That's what we have. Actually, I have some examples of that. So there's also electrical transmission. Transfer is by electric current and electromagnetic radiation. Energy is transferred by electromagnetic waves. That's basically what we call light. So here are the examples. So the first one was, as we looked at, work, right? So energy is transferred to the black by work. You apply force, there's a displacement, and there's an energy transfer because of that applied force. Energy, here's a mechanical waves example. So energy leaves the radio from the speaker by mechanical waves, because that as the sound wave propagates from the speaker into your ear, let's say, what it does, it transfers energy from molecule to molecule to molecule until it reaches your ear. So energy transfer to the, then you have, let's say, a cup of coffee, right? And energy transfer to handle of the spoon by heat. You put a metal spoon inside hot coffee, within seconds, the metal spoon is hot. Why? Because the energy transfer from, hot coffee to the cooler, let's say spoon, and that's the energy transfer going from one object to another. Look at an example for the matter transfer. So energy enters the automobile gas tank by matter transfer. Let's say, you gasoline, right, is, pretty much, chemical, it has chemical energy, and inside your car, then you do chemical reactions, which then, extracts that chemical energy into mechanical energy, which then allows your car to move. Also, you have electrical transmission. So, hair dryer, right? Energy enters the hair dryer by electrical transmission. Okay. Also, the light energy leaves the light bulb by electromagnetic radiation. When the electricity, right? So basically, uh, you know, generally radiation, it means just not a radiation in like a medical term, more of like a radiates. There's a radiate, something radiates in every direction. So electromagnetic radiation means something is radiating in every direction. And that's what the light is, right? Light is an electromagnetic radiation, and we will be seeing that mostly in physics 67. We have like 3 or 4 chapters entirely on what light is and how we work with light. But in any case, so those are the some of the type of energy transfers. So we will be looking at some of them: work, mechanical waves, and heat. Those are the 3 things we will be looking at in physics 66. Now, one of the most fundamental concepts in physics and in all of science is the energy conservation. So again, energy, as you noticed, right, in chapter 6, is a very abstract idea. It's not something we can, see or touch or, collect in a jar or something like that. But it's something that we can calculate. It's some kind of quantity that happens to be sometimes same, before the object does something and after the object does something. That means before and after, that quantity that we call energy can be conserved, which means the same before and after. And that's something we can observe. And there are a lot of conservation laws in physics. There's a conservation of mass, conservation of charge, conservation of current, and so on and so forth. So this is one of those, and we're going to see another one in next chapter, chapter 8. There's also conservation of momentum. So but this is in a way the first conservation law that we are seeing in this class. And this means basically that energy, or this quantity, right, cannot be created or destroyed. Okay, in a way, nothing can be created or destroyed in terms of if you talk about conservation. So that means if the total amount of energy in a system changes, it can only be due to the fact that energy has crossed the boundary of a system by some method of energy transfer. That means, for example, just like this, what you always like to use, right? You have a box at point A. You look at the box and you have kinetic energy plus gravitational potential energy plus spring potential energy, right, at point A. And let's say if I calculate this to be 0, that means energy here is 0. And the only way energy then can change if there is a transfer of energy from some external source. Okay, that's why if you push this with some applied external force, well, you change the energy of the system. All right. So, and this is kind of, what we looked at according to the work done by some kind of, let's say some kind of force. But, as we talked about, there are many other ways of energy transfer. And mathematically speaking, changing the energy of the system equals then sum of this T, where the T here is pretty much the total work done. Or sorry, in a way, it's basically you can say, right? So this T here is the total energy transfer across the system boundary. Okay. So, which means that any type of energy transfer through, let's say, work, mechanical waves, heat, matter transfer, all of those things. So then you have energy of the system, let's say at point A, which is in terms of kinetic potential, gravitational potential, spring potential, electric potential, chemical potential, right? All of those different type of energies, right? So the idea here is that if you're looking at your system energy, the only way you can change the system energy if there is some kind of energy transfer across the system boundary. Okay. So in a way, what we can say, this is, in terms of, let's say you can say T, W, which is work, plus T mechanical waves, plus T heat, right? Plus that. You can say then, all of those things, right? In terms of different type of energy transfer that we can have. That means transfer through the work done, through the mechanical waves, through heat, through matter transfer, and all of those things. And if you have any of those things, right, any type of energy transfer into the system, well, your energy of the system definitely will change. Okay, that's basically given. That means you need to look at in terms of, are there any type of transfer of energy, because the left side of the equation, which is change in energy of the system, is basically can be written in terms of those type of energies: changing kinetic energy plus changing potential energy plus changing internal energy. Okay, those are the type of energies that we have. And the right side of the equation is then work, heat, mechanical waves, the matter transfer, electric transfer, and electromagnetic radiation. Okay, so if any of the terms on the right are zero, the system is an isolated system. Okay, so the work kinetic energy theorem, delta K equals work, is a special case of the more general equation. That means what we're doing in this chapter, for example. Well, in this chapter, we're assuming that, well, we will never be working with, definitely we're not working with electromagnetic radiation or electric, transmission, or matter, transfer, or mechanical wave transfer, or even heat transfer. All of those assuming to be zero. And the only way then system energy, which is combination of changing kinetic plus changing potential plus changing internal energy, will be due to this guy alone, work done. And work is, remember, is just basically some kind of external force pushing or pulling the system, and when the system undergoes some kind of displacement, which in a way, look, you can see, right, it can go into changing kinetic energy or potential energy or internal energy, depending, let's say, type of, let's say, problems you have. Right. So one thing we have here is this. So let's say if I come back to the second part of the left side of the equation, the combination of those two, kinetic and potential, is actually have another name. So we call this mechanical energy. Okay, so we can say as an isolated system is when no energy crosses the system boundary by any method. Okay, so then example of lifting a book is in a gravitational field. What you're doing here is basically you're lifting it, right? So you store some kind of mechanical energy, some kind of gravitational potential energy, and then that gravitational potential energy can be converted into kinetic energy. Okay, so system consists of a book and the earth, and mechanical energy. So mechanical energy at any point of the system is the sum of kinetic and potential. Sum of kinetic and potential. Now, here's what I have important thing about this mechanical energy. If the system is isolated, that means there are no external forces acting, and doing work, then mechanical energy of the system always constant, means change in mechanical energy equals zero, which means mechanical energy, let's say, at some point A is always equals to mechanical energy at some point B. Okay, before and after energy is exactly the same. So mechanical energy is conserved for an isolated system with no non-conservative forces acting. That means when you're dealing with only conservative forces, remember, which are gravity and spring force, then mechanical energy of your system always conserved. Means that you can always say that kinetic energy at point A plus potential energy at point A equals kinetic energy at point B plus potential energy at point B. And remember, potential can be, combination of gravitational and spring potential. But the idea here is that, it's still a potential, right? It's a stored energy. So kinetic plus potential at any point is equal to the kinetic plus potential sum for another point. Okay. This is then conservation of mechanical energy. All right. So now what we're going to be doing then, we're going to be doing a lot of then examples. So in terms of looking at, are there any, mechanical energy conserved and things like that. And remember, so I have some extra, let's say slides on in the notes where it talks about, how to, conceptualize and so on and so forth. It's pretty straightforward. You should be able to read that on your own. But, I'm going to be showing you sort of like, let's say, how to identify if your mechanical energy will be conserved or not in, let's say, in terms of like, let's say, solving some examples. So let's start with, this example over here. So you have 2 kilogram box slides down a long frictionless incline of angle 30 degrees. It starts from rest at time t equals 0 at the top of the incline at the height of 20 meters above the ground. Okay, that's my problem. Basically, here's an incline, 30 degrees incline, and then I start from my object here. But object has a, let's say this is my position A, point A, right? And I can say position of A here is 20 meters, where point B is here at the bottom, and position of B is set then to 0. And we know also that speed at point A is equals to 0, so it starts from rest. Now the question is this: what is the potential energy of the box relative to the ground at t equals 0? Well, I can see that there is a potential energy. There is a gravitational potential energy, but there's no spring potential energy because I just have a box, not an elastic object. And the gravitational potential energy, remember, is mgy. So at point A is just mgya. And since ya is not 0, then I can say it's 2 kilograms times 9.8 times 20 meters. So we get 392 joules. So that's the energy at point A, the gravitational potential energy at point A, because the point A has a height, some kind of, non-zero vertical position relative to my reference position. Part B says, okay, find the kinetic energy and the speed of the box just as it reaches the ground at the bottom of the incline. Basically, reaches point B. Now, one thing I have here is this. The work done on this box as it goes from A to B is basically due to gravity. There's also normal force, but it does not do any work because it's perpendicular to displacement, right? But the gravity does work. But then I know one thing is that when gravity is doing work, then mechanical energy at point A is equal to the mechanical energy at point B, which means mechanical energy at point A is sum of kinetic and potential energies, and mechanical energy at point B is sum of kinetic and potential at point B. And we put like GA, so we know it's a gravitational potential energy. Right. So this is going to be true because, again, the only force is a gravitational force doing work, and it's a conservative force, so mechanical energy is conserved. Now I can simplify this because I know that kinetic energy A, 0, because we start from rest, and then potential energy at B, sorry, this should be B over there. For B is 0 because we reach position where it's, vertical position is 0. That means what I end up with is gravitational potential at point A then equals to kinetic potential at point B. Now, what I have here is then mgya, then this is equals to 1/2 mvb squared. Now, here's another important thing. We can cancel the mass. Mass is unimportant. Any object sliding down 20 meters above the ground actually going to end up having exactly same speed. Because if I rearrange this, speed at B will be then 2 times g times ya, since speed is squared, so take the square root like that. And you can see, right, the only thing the speed depends is the height at point A. So if I plug in the values, right, let's say 2 times, what is it? G here is 9.8, then times 20 meters. Then we're going to get 20 meters per second. Okay. Another way we could have done here, we could have said like kinetic energy at point B is equals to 392 because it's equals to the potential energy, right? Joules, and then use this to solve for the speed, but we would get exactly the same value. Okay. So we can see how easy it is to find the speed at point B. I didn't need to look at, any type of acceleration, try to do force diagram, a free body diagram, and a table, and find the acceleration using the components and things like that, and then use kinematics to find the speed. All I had to do is just understand that the only thing acting on it is gravity, that doing work, which is a conservative force. Then kinetic energy at the bottom equals potential energy at the top, assuming it started from rest. Okay, so very straightforward, easy way of finding the speed at the bottom. Here's another example, which kind of seems like similar thing, but it's a very important difference. Look at the incline. See, it's not like a as basically a straight, smooth surface object going down an incline or something like that. It's actually, look at the surface. It kind of goes like this. Now, if I try to use the dynamics and kinematics for this type of surface, I won't be able to, because it's one thing to know that, okay, so the object going down and the gravity is always constant and it has this theta here, right, and so on and so forth. Another one when the normal force and then gravity constantly changes with respect to its angle and things like that, right? So because the surface is kind of unusual, but from the energy point of view, it doesn't matter. It doesn't matter because all I care about is how high the initial point is, right, compared to my final point, just the height difference. Because one of the important thing about the conservative forces, they are path independent. It doesn't matter how we go from initial point to the final point, as long as we know the height difference between those 2 points. And let's read the problem. While at the country fair, Carrie tries the water slide, whose shape is shown in the figure. And again, it's an unusual shape. So the starting point is 9 meters above the ground. That's it. That's the important thing for me to know. She pushes off with initial speed of 2 meters per second. If slide is frictionless, how fast will Katie be traveling at the bottom? Again, the entire time there's a normal force acting on it. But remember, normal force and tiny displacement that I can see here is always going to be perpendicular. So normal force not doing any work. So who's doing work? Because it's frictionless, gravity again. Which means that the only force doing work entire time is a conservative force, which means energy is conserved. Mechanical energy is conserved. Then I can say, all right, so mechanical energy at A, or this one is actually used like initial. We can just use that, doesn't matter. So initial energy is equal to then the final energy. Then I can say, all right, so kinetic energy initial plus gravitational potential initial equals kinetic energy final plus gravitational energy final. Again, what I can do here is I can set the final position to be vertical position 0. Then this is 0. But then this time the object doesn't start from rest, so kinetic energy initial is not 0. Then what I can say is this: 1 half NV initial square plus MGY initial equals 1 half MV final square. Again, I'm finding how fast it will moving at the bottom, which means V final. All right. Again, I can see that mass cancels out from all the sides. Rearranging this, then, and also multiply all sides by 2. What I will get, and rearranging, I get this. V final square equals V initial square plus 2GY initial. Then taking the square root of both sides, then I can solve for the, initial final speed, which will be 2 meters per second as initial speed square plus 2 times 9.8, then times 9 meters, which is the height. I calculate this and I can find then the final speed to be 13 meters per second. There you go. All right, so that, again, another example where only conservative force is doing work, mechanical energy is conserved. This one just, unusual shape, which shows that it doesn't matter if it goes like this, if it goes like that, or if it goes like this, as long as you're going, from some point A or initial point that has a height difference with respect to point B. Okay. If there was a non-conservative force like friction, then the path actually important, but not for the conservative force like gravity or spring. Here's another example. Right. So this example is, let's say, suppose the pendulum bob. So think like you have a string and some mass attached to the end, and we call that bob. So the mass, we call that pendulum bob. So suppose the pendulum bob has a mass of 0.33 kilogram and is moving to the right at point B. That means we start from this position A. Okay, imagine you have a pendulum just hanging vertically, and then you take it and you move it 35 degrees from that position, right? And then you just let go. Okay, so that means it's moving to the right at point B with the speed of 2.4 meter per second. Um, All right, so never mind. So what actually happens here is we are looking at objects starting at point B with some, speed, initial speed of 2.4 meters per second. Okay. So technically, this is basically, our speed at point B, and it's moving to the right. So then we take air resistance to be negligible, because in this case, air resistance would have been similar as a friction. So that means, it's not a factor in this case. So I want to know, what is the change in the system's gravitational potential energy when the bob reaches point A? All right. So now let's look at in terms of this. One thing I do is I take the position at point B to be my equilibrium position or my reference. I can say position of B equals 0. Then I need to know what is the position of A. So YA. So basically, what is this height? Which is in a way this distance. So that means it represents this distance over here. Because if I have that distance, since I'm taking position of B to be 0, if I know how height the point A is relative to point B, then I can calculate the gravitational potential energy at point A to be just mgya. Okay, mgya. Okay. Now, the way I can do this to find this, technically this delta y, right? So this delta y, I can then use a little bit of, trigonometry, because I know that the length, you can see, right, it's given, right? Length of the string is 1.2 meters. And it goes 35 degrees, in terms of from point B to point A. Now, the same 1.2 meters is here. That means this distance is also 1.2 meters. Now, what I have here is, because it's fixed at this point, and it's when it's moving to the right, it actually goes up a little bit. And this distance, let me make it a different color. So, for example, this distance then can be calculated as the projection of the string when it's 35 degree with respect to the, let's say, vertical position, which means this, you can see, right, this is 1.2. This green part of is actually is, you know so let's say if I take this to be the length, then this is also the length, right? Because now it's 35 degree with respect to that point B, then this will be length cosine theta. That means this portion, right, this portion of the length is L cosine theta. Now, if I have the entire length, that means delta y, right, this little bit of change is equals to the entire length and minus that projection of L cosine theta. Okay, think like this again. So if this is the entire length L, now it goes somewhere over here, 35 degrees. Then what I can do here is I can say, right, okay, so this is the projection of that, which is L cosine theta. And if, since this is L and this is L cosine theta, then their difference will give me then this region, which is L minus L cosine theta. And that's my delta y. That means it's equals to L times 1 minus cosine of theta. That's what I need to do. So this is my YA. So I can then calculate this, right? I can say that my, change in my gravitational potential energy is equals to, since potential energy at point B is 0, I just need to calculate this, mgya, which becomes mg then L 1 minus cosine of theta, because YA is basically my delta Y, because YB is 0, right? And I can calculate this to be, what is it, 0.33 kilograms times 9.8 times 1.2 meters, then times 1 minus cosine of 35 degrees. All right. So we're going to get then zero point 0.7 joules. Right, zero point 0.7 joules. All right. Next, it will be, what is the speed of the bob at point A? All right. So now one thing I have here is this. When it reaches point A, let's say I want to find how fast it's moving over there. That means, we can't really assume that it's going to go to point A and stop. Okay. So because here's what I can do. Let's say, how do I know that it doesn't stop at point A? Well, one thing I can do here is this. Remember, at point B, if I'm looking at energy at point B, is then kinetic energy at point B plus gravitational potential at point B. Since point B is my reference position, that means all of its energy is kinetic, right? All of its energy is kinetic, which will be 1/2 times mass, 0.33, times speed, which is 2.4 meter per second squared. Okay. Now, let's calculate this. Because if I calculate this, so for example, if I calculate this and I get zero point 0.7 joules, that means all of the energy will be converted to potential energy at point A. That means object will stop over there. That means all of my kinetic energy is converted to potential energy. And since there is no kinetic energy, it will have no speed at point A. But if I have a different, if I have different amount, right? Let's say 0.5 or 0.4, that means it does have some kind of potential energy, kinetic energy still at point A. Because let's say what I would do here, I would say that this is equals to kinetic at point A plus gravitational potential at point A. I know that there's a 0.7 gravitational at point A, but I don't know how much kinetic at point B I have, so then I can compare. And let's do this. Now I can, let's say, calculate kinetic energy at point B. All right, so let's do that. So it's 0.5 times 0.33 times 2.4 square. So I get 0.95 joules, 0.95 joules, as you can see, right? So basically at point B, I have 0.95 joules, and at point A, my gravitation is only 0.7 joules, which means, right, which means 0.25 joules then was the kinetic energy at point A. So that's why their sum should be also 0.95. So this is how we can verify if you have a speed at point A or not. Because let's say everything should try to make sense, right? If you're saying, okay, so you go to point A, how fast it's moving. So how do I know it's actually moving? This is how you can verify that. Because I started with 0.95 joules of kinetic energy at point B, but at point A, my potential energy is only 0.7. That means I need to have, also kinetic energy to compensate and make the sum as 0.95. And this is what we can do. In a way, you can say, right, I can rearrange, even though right now I know already kind of by subtraction, right, how much kinetic energy what I have. But this is what we can do. We can say, all right, so here's what I have. I have kinetic energy at B equals to then kinetic energy at A plus gravitational potential at A. Okay. So what I have here is, and I can say, all right, kinetic energy at A is equals to kinetic energy at B minus gravitational at A, which, since we calculated this 0.95 joules minus 0.7 joules, we can say, right, it's 0.25 joules. Then I can say that kinetic energy then is 1/2 m speed at A square. So then I can rearrange and say, okay, speed at A is equals to square root of 2 times 0.25 joules divided by the mass, 0.33. And I can then calculate, I can calculate my speed, which is 1.2 meter per second. All right, so I did a little bit different from the slides, so you guys can compare and see, whatever works for you. I just wanted to give you always, if I can, a little bit of different, ways of looking at things. All right, so then here's what I have for part C. It says, if the mass of the bob is increased, does your answer in part A increase, decrease, or stay the same? Well, remember, this was my part A. And what I calculated, 0.7 joules, that was based on, also the mass of the object. So obviously, if you make it bigger, my answer in part A will increase, which will be 0.7 joules. So which was 0.7 joules, but if you make the mass bigger, gravitational potential energy will increase. The next one, part D, says, if the mass of the bob is increased, does your answer to part B increase, decrease, all the same? That means in terms of my speed, Will it change? Well, in this case, it won't. In this case, it won't. Because remember, if you look at just this equation, right? This is 1 half mvb square. Let me do a different color so you guys can see this is complete. So, for example, 1 half mvb square equals 1 half mva square plus mgya, right? This was my equation. But, you can see from here clearly that mass cancels. That means it doesn't matter what the mass is. You can double, you can triple, you can whatever, you're still going to get the same speed. Gravitational potential energy increases, yes, but equivalently, the kinetic energy increases by the same amount. So then, they pretty much cancel each other's effect. So speed always going to be the same regardless of the mass. All right, here's another example. All right, so 0.14 kilogram block slides with a speed of 0.95 meter per second on a frictionless horizontal surface until it encounters a spring with the force constant of 735 newtons per meters. The block comes to rest after compressing the spring 4.15 centimeters. Find the spring potential energy U, the kinetic energy of the block K, and the total mechanical energy of the system E for the compressions of, let's say, when it starts compressing, right? So let's take, in terms of when it's compressed of the 0 centimeters and then also 1 centimeters. Okay. All right, so it seems like we're given different things. We first say that, okay, so let's say here's a picture. So let's say here's a spring sitting in equilibrium, x equals 0. And then you have a block moving like this with some velocity. Okay. So let's say here's a block moving with some velocity. Assuming that this velocity here, this is the speed, right? It's constant. So 0.95 meter per second. Then what happens here is this. When it comes and reaches the spring, it is still moving with the same speed. But then as soon as it hits the spring and starts compressing, remember there's a restoring force acting on it, right? And this restoring force gonna, slow it down and stop. Or we can say now what happens here is that, whatever the, kinetic energy the block has, then all that, kinetic energy then eventually is transferred, converted into spring potential energy. And what it tells you that this block then gonna compress the spring to 4.15 centimeters until it fully stops. That means this is the maximum compression, comes to rest, right? It's gonna compress, stop, and do that. That means one of the things we can do, we can say that, all right, so this is point A, which is point A is the point where right at, when it makes contact with the spring. Point B here is the, maximum compression where it, comes to rest. All right, so let's see what we have. We're told it's a frictionless horizontal surface. That means here there's only normal force and gravity, and both of them not doing work because let's say object is moving to the right, so displacement is perpendicular to those forces. Then when it reaches the spring and then hits the spring, the only force acting in is the spring force. Spring force then does work because it's acting in opposite direction of displacement. But then spring force is a conservative force. That means mechanical energy will be conserved before and after. That means I can say mechanical energy at point A is equals to mechanical energy at point B, which means Ka plus U spring A. I don't have to worry about the gravitational potential energy here because point A and B have the same vertical height. So that means there is no change in gravitational potential energy. I can just ignore that. Equals NKB plus U spring B. Okay. Now, there are several things I know that this, if I'm using this in calculating, right? So this becomes 1 half MVA square plus 1 half KXA square equals 1 half MVB square plus 1 half KXB square. Those are the equations. Well, I know one thing, that point A has x equals 0. So this is 0. And at point B, it comes to rest. So that's 0. That means what I have here is, you can see, right? In terms of 1 half mva square, which is my kinetic energy at point A, then is equals to 1 half kx b square. That means all of my kinetic energy at point A will be converted to the potential energy at point B. And what we want to know here is we find what is the spring potential energy U. All right. So I can technically calculate that two different ways because the potential energy is equal to the kinetic energy. I can solve for kinetic energy because I have that, right? See, kinetic energy at point A is equals to 1 half times mass times speed at A square. All right. So it's 1 half times 1.4 kilograms times 0.95 meter per second square. Kinetic energy at point A is 0.632 joules, which is, one of the things I needed to calculate anyways. And since they are equal to one another, I can just say that, potential energy is equals to 0.632. But I can also calculate this, right? 1 half times 734 newtons over per meters, and then times 0.0415 meters square. And guess what I'm going to get? I'm going to get 0.632 joules. Exactly same thing. All right. Now, what is the total mechanical energy of the system? Well, mechanical energy of the system is equals to, well, at point A is just kinetic energy, but it's also equals to point B, right? Which is just gravity in spring potential energy. But all of them are pretty much equals 0.632 joules. That means that's my total energy because I have 2 points, and each point, my energy either pure kinetic or pure potential. That means total energy is 0.632 joules. Now let's look at part A. It says now what are those quantities at point A, specifically at point A? Well, I can say this. My potential energy at point A, which again, we kind of talked about that, right, is 0. If, because X is 0, my kinetic energy is 0.632 joules, then my energy total is 0.632 joules. About part B, what is my potential energy at, sorry, not point, this is actually point C, because, part A was actually talking about point A specifically because, that's the point of contact. But point B, part B, asking about some random point C, which is somewhere over here, right? 1 centimeters instead of like 0.15, which was the maximum displacement. So here I actually have to calculate is 1 half times 734 newtons per meters, then times 0.01 meters square. Okay, so what I will calculate is 0.0367 joules. All right. That means this is my potential energy at point C. Now the question is my kinetic energy is also equals to point 0.036 joules? Well, no, because remember then at point C, which is somewhere over there, I do have, so you can see, right? So my energy at point C is kinetic at C plus potential at C. But because energy is conserved, total energy at point C is equal to total energy at point A, which is equals to 0.632 joules. Now, that means what I have here is then this is kinetic energy at C plus potential energy, which was 0.036 joules, which is calculated, right? This is 7. Then I can just rearrange, right? And just solve for kinetic energy at point C. Just rearrange and calculate. Then we will see that 0.595 joules. There we go. So this is gravitational potential energy. This is total energy, right? Because, total energy is still, the same everywhere. and we can then use that to find the kinetic energy. All right, so next what we're going to do here is we're going to look at how we can change the mechanical energy of the system. So let's say what changes mechanical energy of the system. So in a way, we can look at then this internal energy. Remember, in a way, you have the energy of the system. You can say then this is equal to the change in mechanical energy, then plus change in internal energy, right? Change in internal energy. And this is then equals to then, some of the, all of those other, uh, work done, let's say. Now, one thing we have here is this. Okay, so this internal energy, change in internal energy, is actually due to the, directly friction, because internal energy means that when there's a kinetic friction involved, some of the mechanical energy technically then can be converted into, internal energy. Okay, that's why the object sliding on a rough surface slows down and stops, because, let's say you can see, right, as the object, as this book is moving to the right with some speed, if the surface is rough, there's a friction acting in the opposite direction of displacement, which gives you then work done by the friction, kinetic friction, as negative. That means it will then dissipate energy, right? So, or remove energy. That means, energy, will then decrease, kinetic energy will decrease, your initial velocity will eventually go to zero, because all the kinetic energy, right, will be then converted to heat energy, because that's what friction does. It transfers energy into like heat energy, and heat energy, basically, you cannot take it back. So whenever object is sliding, right? So whenever object is sliding, you can say that the change in kinetic energy is equal to the work done by all forces other than friction minus the energy associated with the friction force. In a way, you have kind of like this equation. So work done by other forces, which can be like, let's say, a push, pull, tension, and things like that, minus kinetic friction equals delta K. If this is zero, the only thing acting is the friction, then you can say then just ignore this. So then you have this negative FKD equals delta K, which means work done by, kinetic friction equals delta K, where this guy is basically a non-conservative force, and it actually changes the energy of the system. Okay, right? The friction force transform kinetic energy in a system to internal energy. The increase in internal energy of the system is equal to its decrease in kinetic energy, and internal energy is always only increases, because you have, let's say, no internal energy to start with. It only increases because the kinetic energy is converted to internal energy, but you cannot go other way around. Internal energy cannot be converted to kinetic energy, so it's always kind of like one way freeway. So now let's look at sort of like, let's say, what I just talked about, right? So you have mechanical energy, change in mechanical energy, which is in terms of delta K plus delta U, right? And what we can say here is then you can change the mechanical energy by, doing work, due to friction. Okay, so if friction is acting within an isolated system, then delta E is mechanical equal delta K plus delta U, and this is no longer equals to zero. See, change in mechanical energy before, which was delta K plus delta U, was equals to zero in an isolated system if there was no friction. But if there is a friction, then you can say that it's equals to the work done by the friction, which is negative FKD. These are how much distance it will travel, when the friction is acting on it, and this is the magnitude of the friction. Okay. So delta U is the change in all forms of potential energies, gravitational, spring and things like that. And if the system in which non-conservative forces act in non-isolated, and the external influence of the system is by means of work, then we have change in mechanical energy equals the work done by friction plus work done by other, by other non-conservative forces. In a way, we're kind of separating friction from other non-conservative forces, even though it is also a non-conservative force. This is the only type of non-conservative force that will go into changing internal energy. These guys have nothing to do with internal energy. Friction then converts energy into internal energy, So that's why it's kind of a little bit separated. All right, so think like this. So we study the physical situation carefully and form a mental representation of what's happening. Is it only conservative forces or non-conservative forces? And if it's non-conservative forces, what type? Friction or push or pull or tension or thing like that, right? So you can basically understand what's going on. Because you can, right? So delta E mechanical is equals to then work done by friction plus work done by all the other non-conservative forces. So if this is zero, then energy is conserved. That means only conservative forces doing work. If this is zero, but let's say there's a friction, then you have this, which is, mechanical energy will change by the same amount as the work done by the friction. If you have friction plus other things, then you have that giant equation where you can take everything then into account. Okay, so that's kind of thing. So you have to take everything into account depending what we have. So that's what pretty much all of this talks about. So in a way, you start with this equation if you want, and then you can say, can I eliminate this? Can I eliminate that? If I can eliminate then is this is equals to zero. But if I can't, then I have to, put that part of my equations and things like that. So you need to be reading carefully, reading several times the problems and understanding, let's say, what are you, working with, what are you dealing with. So that's why analyze, choose configuration and things like that. So in a way, go ahead and read this, on your own to allow you to understand how to work, how to set up your equation, what factors to take into account, and so on and so forth. But as I said, right? So in a way, you can take, think of like this is your equation, right? So in a way, if you take this part of that, so then this becomes, let's say, energy of the system, which is, change in mechanical energy plus change in internal energy, which is due to friction, right? Then this is equals to the work done by all the other non-conservative forces. Okay. So in a way, this is can be part of your energy of the system. Okay. If you take the surface part of your system, for example, because if the surface is part of your system, then all you can do is understand that just some of the kinetic energy just, goes into, let's say, um, thermal energy or like, internal energy. All right. So make sure your results are consistent with your mental representation and things like that. All right. So now um, I'm going to start basically showing you several examples with friction or with some kind of non-conservative forces. And you should be able to then see the difference, compared to those first four problems that I did with only conservative forces. Right, so let's look at this. A 2.5 kilogram textbook is forced against a horizontal spring of negligible mass and force constant 250 newtons per meter, compressing the spring a distance of 0.25 meters. When released, the textbook slides on a horizontal tabletop with a coefficient of kinetic friction where mu k, this is just mu, where mu k is equals to 0.3. Use the work energy theorem to find how far the textbook moves from its initial position before it comes to rest. All right. So I have a picture over here, right? So think like this. So what we do here is we compress. So it's compressed basically to a distance of 0.25, and the book here is 2.5 kilogram, and the spring constant is 250 newtons per meters. A lot of two and fives. But what we have here is then this. We then understand that this is, let's say, going to be point A. Okay. Then here's what I have. You can also think like this. This is what we end up. So the spring, because the book is not attached, but it's just used to, just compress, right? They just, you just take the textbook and push the spring, and then when you let go, then the spring will try to go back to its equilibrium position. I don't know. Let's call the equilibrium position point P. So then it's going to reach its equilibrium position. Then after that, because the book is not attached, then the spring will stay there, but then the book will move with some speed at B. Okay. And then because the surface is basically rough, right? It's rough basically in the entire time. So, let's say then it's going to go eventually reach some point C, and then it's going to stop. That means, one thing I can do here is it says 1 and 2, but I rather do this in terms of, let's say this is point A and this is point C right then. Okay. So that means its speed is 0 at point A and its speed is 0 at point C. Okay. So now what I have here is then this. Okay. So I know that work done, remember the total work done, right, was equals to the change in kinetic energy. This was my um, work kinetic energy theorem. This is always true. Um, Now, one of the things we can do here is think of it like this. So what is the kinetic energy at point A, point B, point C? At point A, I know it's 0. Point B, it's some value, non-zero. But point C is also 0. Then what I can do here is I can just ignore point B, and I can say, you know what I'm going to do here is I'm going to just take point A. Right. I'm going to take point A and point C as points of interest. And I'm going to be looking at that, going from A to C. All right. And during that time, going from A to C, right, the work done on the system, right, the total part of this, right, there were two forces doing work. Work was done by friction, kinetic friction, and there was a work done by the spring force. And this is equals to delta K. But this is the delta K between point A and C, for which both of them speed is 0. That means my delta K is 0. All right, my delta K is 0, which means the sum of work done by the kinetic friction plus work done by the spring, well, should be 0. I know what is the work done by the spring is 1/2 kx squared, and the work done by the kinetic friction, which is then minus fk times d. All right. So then the question here is this: what is that distance d? Right. So what is that distance d? In a way, I guess you can see, right? I'm taking the point A and point C from the center of the block, so it's okay. Let's take that. Well, you can see, right? It's important to understand that x is not equals to d. X was given to us, but x is by how much it was compressed. But d here is the distance from A to C. All right. That means what I have to do here is, I understand then I just need to, like, let's say, in order for me to find d, what I end up here is this, right? Work done by the kinetic friction plus work done by the spring is equals to 0. This is negative fkd plus 1/2 kx squared equals 0. Okay. Then I can rearrange this, right? Rearrange this. By the way, let's say, what is the f of k? Well, remember, f of k is equals to negative mu k times normal force. And because it's a flat surface, normal force is equals to just mg. So it's, normal force is just basically replaced with mg. So negative mu k mg times d, then plus 1/2 kx squared. All right. So now I can rearrange this, right? I can rearrange this and just solve for d. So this will be equals to k times x squared divided by 2 times mu k, because negative will cancel out as I move the other one to the right. So mu k times m times g. Okay. Then this will be 250 times 0.25 newtons per meters. So then 2 times 0.34 mu k, then 2.5 for the mass, 9.8 for the acceleration, and we're going to get 1.1 meters. That means that's the distance it will travel until it stops. Okay. So that means, this is another way, we can actually, solve this problem. All right. So interesting problem. Here's another one, which is, again, and a problem, a very nice problem, where before maybe we could have used this. Actually, we could solve this using kinematics and dynamics. But we can see that problem like this, we can also solve, using energy method, energy approach. All right, so let's see what we have. At the construction site, the 65-kilogram bucket of concrete hangs from a light but strong cable, which means it's a massless string. It's good. That passes over a light friction-free pulley and is connected to an 80-kilogram box on a horizontal roof. The cable pulls horizontally on the box and a 50-kilogram bag of gravel rests on top of the box. Okay. Now, the coefficient of friction between the box and the roof are shown. So the static coefficient friction is 0.7 and kinetic is 0.4. Now, find the friction force on the bag of gravel and on the box. Okay. So let's see what we have. The idea is that what you have is there's the, I don't the way I would probably do, in terms of, because both of them, let's say, in terms of, like, let's say the notation, right, the subscript. So I can say that this is the mass of the, um, let's call this object 1, and let's call this object 2. Probably easiest like this. So now here's what I have. Mass of object 1 is then equals to the mass of the box plus mass of the gravel, which will be then 80 kilograms the box plus then 50 kilogram bag of gravel. So then 130 kilograms. That's my mass 1. And the question here is this. All right, so here I have M2G pulling it down, and there's obviously the tension, and then the same tension acting on the, M1, right? My mass 1, which is the combination of gravel and the on the box. The question is that, will the tension be strong enough to pull the gravel? Okay, right. So that means I wanna be able to, let's say, calculate that first. Okay, let's do this. So I want to calculate, let's say, weight of the, this concrete bucket, right? So I can calculate basically M2G, see if it's, strong enough or something like that. All right, so if I calculate this, right? So if I calculate M2G, which is in terms of 65 kilograms times 9.8, I'm gonna get 637 newtons. The question is that means, this is, how much the weight is pulling, which should be then stronger than tension. And then the tension, that means, will be, has to be stronger than the, friction. Let's see how much is the friction, like, let's say, maximum static friction. Because if it's like much smaller than 637, then we should be fine. Let's do this then. I know that static friction is equals to mu s times normal force. But if the M1 is at rest, sitting there on a horizontal surface, then normal force is equals to the M1G. That means it's equals to mu s times M1G, which is equals to 0.7 static friction, kinetic friction, right? Times 130 kilograms for the total mass times 9.8. And here's what I get. 892 newtons, way stronger than the weight of the bucket, which means that, the system is at rest. Nothing, you won't move that. That means at this instant, right, with the box and the gravel together, system just sits there at rest. So part A is that find the friction force on the back of the gravel and on the box. Well, the friction force right now is 637 newtons. Why? Because if the system is in equilibrium, then tension is equals to M2G. And if the tension is, basically 637 newtons, it's also here 637 newtons. That means the box and gravel together can push with the static friction of the same, right, 637, to keep the system in equilibrium. All right. That's why part B, it says, all right, so suddenly a worker picks up the bag of gravel. What happens then? Well, what happens then is this. What is the static friction now? Well, it's zero point 0.7 times, instead of 130, is only 80. So 80 kilograms times 9.8. And if I do this, right, I should get, let's see. All right, so I'm getting 500, let's say 49 newtons, which is way less than this. That means as soon as we pick up the gravel, the system is accelerating. That means it's going to then move, which means that static friction is no longer strong enough. So then you're basically after that pretty much dealing with the kinetic friction. Right? So you're dealing afterward with a kinetic friction. All right. Now what happens here is then the system starts moving. So I'm going to go back. And what we're going to see here is that right now my M1 is just 80 kilograms, right? Because the gravel is no longer there. And here's what I have. I'm going to now use energy approach to represent this. It says, suddenly a worker picks up the bag of gravel. Use energy conservation to find the speed of the bucket after it has descended 2 meters from rest. Okay. That means now the bucket, right? This is being, let's say, the ground, or, let's say, assuming that the ground, let's say 2 meters below that, is going to go and hit the ground. And we want to know, let's say, what is the speed? Okay. Now I'm gonna say then this my system, let's say let's say E1, right, is the instant when when we pick up the gravel. All right. And what I have here is basically my energy. I'm gonna, you can look at each one separately and kind of combine them, or I'm actually gonna take both of them together. Right. So I'm gonna take both of them together, and I'm gonna say that my energy of the system, right? Energy of the system, let's say mechanical energy, will be then equals to then the work done by the friction. Because there's a friction, right? My energy, mechanical energy, will be changed by the friction, equals the work done by the friction. So which means this. That means energy, let's say energy 2 minus energy 1, you can just do it like that, right? Is then equals to the work done by the friction. Okay. Which means then what I have here is I can rearrange it and say, all right, so if I move it to the other side, becomes energy 1 plus work done by the friction is then equals to my energy 2. Right? That means, energy 1 plus work done by friction equals energy 2. Okay. Now then, here's what I have. I have two objects in my system. That means when I'm talking about energy, right? So it will be, all right, so kinetic energy of one, let's say, object 1, or maybe, sorry guys, maybe like 1 and 2 is wrong to say because I'm using 1 and 2 for the object. So let's do this. Let me use A and B like that. So this is B, this is A. So this is A and this is B. Okay, that means final EB minus EA equals work done by the friction. So energy at point A plus work done by friction equals energy at point. So because what I have here, I have two objects, object 1 and object 2. So my energy at point A is then kinetic energy of object 1, which is, at point A, plus kinetic energy of object 2 at point A, then plus gravitational potential of the object, 1 at A, then plus gravitational potential of object 2 at A. I can ignore spring because there are no spring. Then plus work done by the friction. Then this is equals to then kinetic energy of object 2 at point B, and point B is then when it hits the ground. Then plus kinetic energy object 2 at point B, then plus gravitational potential object of 1 at B, plus then gravitational potential object 2 at B. I know it's kind of like handful, but actually it's pretty straightforward. That means you just have kinetic plus potential, but just 2 for each one, right? And you can see, right, we're going to be greatly simplifying this, because here's what I have. Remember, both of them starts from rest. That means none of them have initial kinetic energy. And what I'm going to do, I'm going to take position B to be 0. Position 2B to be 0. But here's what I have. See, if I'm looking at the gravitational potential energy of the box, which is my object one, right? See, it's going to be then when the concrete, right, when the M2, object two, goes down by 2 meters, this guy then goes to the right by 2 meters. Exactly same displacement, 2 meters, but to the right, which means that object one, the box, doesn't change its height. That means those two values are the same, so I can kind of get rid of them because there's no change in gravitational potential energy for the box. Concrete undergoes a gravitational potential energy difference, right? It has height difference, and point B is going to be then zero, so this guy here is zero. You can see, right? I greatly, you know, simplified my equation. All I have here now is this. There's a gravitational potential energy of the concrete, right, of the bucket, and there's a work done by the friction on the box. Both of them then moving at point B. So then what I can do here is find that. And also one important thing, because both of them, remember, in a example like this using Newtonian dynamics, they have the same acceleration. Well, if they have the same acceleration and they both start from rest, that means that anytime they have the same speed. Okay, which means I can say this: m m2 g y a, which is gravitational potential energy of 2 at a, then minus work done by the friction, which is Fk times d, right? Fk times d. Then this is equals to then 1/2 m1 vb square plus 1/2 m2 vb square. All right, but they have basically both of them have the same speed. So in a way, this is 1/2 m1 plus m2 vb square. Okay. All right. So what I have here is f of k will be replaced, right? So this f of k over here will be replaced with, mu k times m1g, because again, the normal force is just the weight of the box, right? And then I have everything, right? I have the mass one, mass two, I have the distance, right? D is 2 meters, and this YA is 2 meters. Those are, pretty much the same, right? As I mentioned. And the only thing that basically we don't have is speed B. And then, just plug in everything, rearrange and calculate this VB, you're going to get 2.99 meter per second. Okay. Again, you can try to follow. If you're unable to follow, I have in the lecture notes, right? I have the full solution. All right. So you can see, right, this problem you can do using energy approach or using the Newtonian dynamics and kinematics. You just, to me, if you really understand this, if you're able to digest this is actually simpler. The last thing we have in this chapter is the rate at which we transfer energy. So let's say we transfer energy or energy changes. Okay, but how long does it take? Does it take 5 hours, 5 seconds, 5 minutes? So we are looking at the time rate of the energy transfer, and we call that power. So the power is equals to dE dt, or in a way it's the work dt, kind of same idea, right? Because work is the energy. This is instantaneous. You can also look at average, which is then the work done divided by delta t. Okay, so like let's say work done divided by delta t, or change in energy divided by delta t. Also, we can think like this. If I come back here and say, okay, work done, which also you can see, right, is force times displacement divided by delta t, then I can combine delta x over delta t, which is then the speed, right, the velocity. Then I can say it's force times velocity. Okay, so you can write over here. So in a way, there's another equation for the average power, which is force times velocity, but it's a product of two vectors, so it's technically a dot product. Okay. The SI unit for the power is joules per second, which is how many joules per second, right? Because work over time, but we define that to be watt. So 1 watt, or let's say 1 watt is 1 joule each second. And there are two types of let's say units for the power. A SI unit is watt, but there's also horsepower that we use in US. And here's a conversion: 1 horsepower is 746 watt. There's also kilowatt hour, which is actually not a unit for the power, but unit for the energy. Because think like this: here's energy over time. Remember, is the power. So then, if you multiply both sides by T, then you get energy. So energy equals power times time, which is watt times seconds, right? But if you rearrange, becomes kilowatt hour. This is something that you use, let's say, to calculate amount of energy, let's say usage in your houses and things like that. All right, so here's one last example. So an elevator car has a mass of 1600 kilogram and is carrying passengers having a combined mass of 200 kilogram. A constant friction force of 4,000 Newton retards its motion. How much power must the motor deliver to lift the elevator car and its passengers at a constant speed of 3 meters per second? So this is a little bit of, combining dynamics, doing dynamics, because what we have here is there's a tension up and there's the weight. Let me put like as a gravitational force, right? But there's also, we are told that there's there's some kind of, retarding friction force. So we have that. So, but it is speeding up, right? Sorry, it's moving at constant speed, which means that net force in the y direction is tension minus friction minus, gravitational force equals 0. Okay. That means I can then solve for the tension, which is friction plus then weight. And we have that, right? So we have, this is 4,000 newtons, then plus 1600 times 9.8. So in a way I can calculate this, right? In terms of what is the value. All right, so if I calculate, this is 19,680 newtons. And then what I can do here is this, because so technically it says how much power must the motor deliver to lift, and what's lifting is pretty much this tension, right? So then I can solve for the power as the, tension times velocity, basically the dot product of those, right? So then I can just say it's okay, 19,680 times velocity of 3 meters per second. Then the power here is 6.49 times 10 to the 4 watts. Okay, so basically this is times 3. Um, and we can get that in terms of this value. Okay. All right, so I think I have a little bit of typo in my slides. So technically this should have been an 1800 rather than 1600. So the number is slightly different, but that's pretty much the same idea is the same. All right, so this pretty much concludes chapter 7.